So yes, I'd like to talk about something very different. Never really worked in anything related to reinforcement learning. I've actually worked a lot in applications to neuroscience, but I decided I wouldn't focus on this because I think few people do neuroscience in the room. One thing, I guess, what I want to focus on is that we've learned over the years to deal well with learning with extremely high dimensional data and limited amount of observations. And I think there are take-home messages there that are quite general. And so I'll be talking about two different points of view on this. And really, so the settings are very high dimensionality. And what we've seen is that in a variety of applications, there's similar solutions. And so the data may be extremely different. You may be looking at signal data like high-dimensional images, spectra. You may be looking at many entities. That will blow up your dimensionality, and this is the kind of stuff you have in recommender systems. Or you may be looking at categorical data where it's high-dimensional because you have many categories because they've not been standardized. And so I'll be basically looking at these different problems. And the key idea is that you're going to have to find and exploit links and redundancy across those features. Right? You have extremely high dimensional space. You just don't have enough data to get the most of each feature. And that goes very fast. I mean, if you have 100,000 features to get enough data to use well all those features, you'd need millions of examples. And so you really need to exploit those redundancies. And I'll be talking about two different ways of exploiting those redundancies. One is matrix factorization. And here, the focus of my talk is going to be about scalability, and hence a specific algorithmic work that we've done to scale better. And in the second part, I'll be really switching gears. It's basically two related talks. I'll be talking about some work on using similarities to do encoding. And it's work that seems trivial, and I believe is not, and I'll talk about it, why it's not at the end. So factorizing huge matrices. So this is really work that's been led by Arthur Mensch, who's my student, with Julien Méral and Bertrand Thirion, and it's been published in two papers, one at ICML and one long version. And they have overlap, but they also talk about different things. So they're both interesting, I hope. And so I'd like to talk first about intuitions, then show the experiments, then to go through the algorithm and the ideas of the proof of why this works. The last two bits have a bit of math, but I'll try to get some intuitions looking at the math. So real-world data, one typical application would be recommender systems. So I know very little about recommender systems, but basically one of the challenges I see from the algorithmic standpoint is that it's a matrix that's extremely large in both dimensions. It's extremely large matrix in both dimensions. It is a sparse matrix, which makes things better. Now in brain imaging, which is what I do mostly, we're starting to have situations, so we're looking at things like the activity of the brain at rest, and we're doing a lot of things on this. We're doing diagnosis on this, and we're starting to have the situation where we have extremely large cohorts with thousands of subjects. Each of those subjects have many samples, so we're looking at a huge number of samples, we're looking at the million-size sample, and each image has itself a very large dimensionality, so 100,000 features. The challenge here is that the data is dense. So if you look at the size of the matrix compared to a recommender system, it's not huge. But now, look at the size in terms of number of elements row-wise and column-wise. But now if you look at the space on disk, it's pretty big. It's dense, okay? And we've used matrix factorizations or dictionary learning on these data for a long time, and they work extremely well. But the challenge here was, can we reduce the cost here? And so the overall idea is that, so we can see this as a minimization problem, and the overall idea is that we're minimizing a cost function with standard matrix factorization cost function, and there's going to be some form of penalty. And for my applications, I often care about L1 penalties, but this could be L2. And one thing I didn't put here is that we're going to need some constraints on E when we minimize this to have the problem well constrained. Okay? And so the naive way of doing it would be to tackle this as an alternated minimization problem where you decrease over E, you decrease over S, you decrease over E. Now this doesn't scale well at all because you're just going over your data all the time. So if your data doesn't fit in the memory, you're just loading it, dumping it, loading it, dumping it. So that's the naive way. Good news is there are other ways of doing this. And one nice way of doing this is to rewrite this problem as an expectation. So basically, we're separating those two variables, and we're separating a sum over one direction of the matrix, which we call the samples, and we're saying that this sum, because we're summing over many samples, we're viewing this as an expectation. In which case, we can tackle this with stochastic solvers, and the key idea of stochastic solvers is basically we're going to approximate this expectation, okay? And so this is work that's been done by Julien Méral and is pretty much state-of-the-art for dictionary learning when you have many samples. And so really the idea, it gives you what's been known as online matrix factorization, is that you're going through your matrix, and you're looking at one column at a time, or many batches of column, and then you're optimizing over the other problem, and you're doing this over and over again. So basically, you're streaming. This works extremely well when you have very anisotropic matrix. So it's extremely efficient. The problem that we have is that our matrices are not very anisotropic. That said, this allows us to tackle our problem. If we have 2 terabytes of data, now we can fit this on 2 terabytes of data. And so this is brain data. For brain experts, this looks pretty because this is really outlined subregions of the brain in an unsupervised way. Now, the goal of this slide is to say that the amount of data really matters. Because now if we take a fraction of the data, we get result that qualitatively isn't as nice, but we of course have a much better runtime. So can we go a step further? Yes, we can. And the way we can do this is to say, well, my matrix is big both ways, so I can do stochastic approximations in both directions. Okay? So I'll give you the math that goes behind this. But really the idea is that as we move forward, we're only looking at a fraction of the features. And because the features are correlated, when we're only looking at a fraction of the features, we still are going to capture the essential information, and we still can converge. It's not trivial. So we've called this approach subsample online matrix factorization. So empirically, it gives us this here. We're able to tackle much more data, 10 times more data, in the same amount of time. And we're kind of cheating because we're not looking at all the data. We're only taking subsamples of the feature. But qualitatively, this looks much better for the same computing budget. So this is a quantitative result. How do we evaluate this in a more formal way? And the right way to look at those online algorithms is to look at some form of test data, left out data, because those online algorithms, those stochastic algorithms, they're really minimizing the expectation of a loss, right? So we don't have the expectation of the loss, but we can look at left out data and compute this loss on the left out data, right? So here, if we're streaming in one direction, it means that we take a subset of those columns, we leave them out, and as the algorithm progresses, we check that the cost on this subset decreases. So what I'm showing you here is comparison to classic methods. In light blue, we have the standard approach of online matrix factorization, the one that we modified. In purple here, we have our approach. So as a function, importantly, this is a function of time. I care about time, I don't care about iterations. Okay? And these are all implemented by the same person with the same optimization. This is a fair comparison. And so what we're seeing is that we're decreasing much faster. And here we've also compared to stochastic gradient descent, because another approach is to say, this is a minimization problem, I can solve it with stochastic gradient descent. And so what we're doing is not a stochastic gradient descent, it cannot be cast in the framework of stochastic gradient descent, and I'll come back to it because it's important. What we're seeing is that we're getting significantly faster. This is, by the way, a log scale in time. We always plot our time measurements in log scale. So these improvements are important. So importantly, this does not only work for very large brain imaging data. Here I've shown you the results for other kind of signals. So these two problems are brain imaging data, but this one is a much, much smaller one. So it's a much, much smaller one. We're still getting noise speedups, but not as large. Okay? And here we have a non-negative matrix factorization problem. So using the same framework on, this is hyperspectral imaging. Okay, so another kind of data. What's important basically is the data needs to be high dimensional. So typically natural images in pictures are not high dimensional, and the reason is that people use patches, and patches are small. Okay, so the techniques that are developed for these don't work well on very high dimensional data. And this is also dictionary learning, and so what we're not showing here is that we're playing between the constraint set and the penalty to put sparsity on one end, on the other end, not sparsity. We can play with this to address a family of problems. So sparse PCA, non-negative matrix factorization, they're all in the same framework. So it's reasonably versatile. And each time we're getting comfortable gains. We can also apply this to recommender systems, and here there's a bit of a caveat, is that in recommender system, you're actually masking the cost and your loss. You don't want to minimize the error between your low rank matrix factorization and the non-observed data. So the equation is actually slightly different, okay? And it falls in a slightly different theoretical framework. And the proofs that I'm gonna show after don't apply to recommender systems. But in practice, this does work quite well. And here we're comparing to a state-of-the-art coordinate descent. So it's a randomized coordinate descent solver. So it's basically the same class of solvers than stochastic gradient descent. And basically, the bigger the data set, the bigger the gain. Okay? So now let me dig in the algorithm, and if you will, please bear with me. I know there are many formulas, but hopefully you're going to get some intuitions there. So the prior art by Julien Méral, basically the standard algorithm to tackle online matrix factorization, works the following way. As I said, you're going to stream samples, and then you're going to solve one end of the problem. So we're going to compute what we call the code. So it's one of the two matrices. And this is a standard, basically it's a regression problem. So it can be a sparse regression problem, it can be a non-negative regression problem. And then you compute the other part of the cost, which we call the surrogate function, which is you fix A in the equation, and this looks like this. And basically, this is nicely differentiable, so you can solve it easily. And importantly, you can aggregate here sufficient statistics of your problem. So that's a nice difference compared to stochastic gradient descent, is that as we go, we're aggregating sufficient statistics of this function. And then you minimize it relative to D, okay? So it's a bit like a stochastic alternated minimization. So why am I calling this a surrogate function? And the reason I'm calling this the surrogate function is that we're not really minimizing the function that we would like to minimize, because the function that we would like to minimize when we're minimizing on D would be for the optimum alpha. And we don't have the optimum alpha. we have alpha that is suboptimum. So this is a surrogate function, and because alpha is suboptimum, it's actually a function that is above the function that we're trying to minimize. So really, the theoretical framework to analyze those algorithms is the framework of stochastic majorization minimization. Okay, what we have here is a majorization minimization approach. So this is why it's something that is quite different from a stochastic gradient descent. Okay, and if maybe there's one take-home message from this talk is stochastic majorization minimization approaches are interesting. Now, I find the paper by Julien Meral that presents them extremely hard to read. But they're interesting. And really the interesting reason is that the hyperparameters are much, much better behaved than those for stochastic gradient descent. Okay, so this is the standard algorithm. And now what we're going to do is that we're going to add subsampling to it. And the idea is that basically here, the complexity of all these steps actually depends on P, on the number of features. And if P is very large, all these steps become extremely costly. So intuitively, what we're going to do is that we're going to stream the data. Each time we're going to consider a subset of the features, which we can formalize as basically masking the data. And then, so we get a reduced dimension. And then we're going to use only the masked data in the computation. And the challenge is, how do we modify all steps to work only on S features? Now, this was the intuition we started from. And it works, but it turns out it's suboptimal. And I'll give you maybe a few more details. So now this is the most horrible slide I have, so please bear with me. And on top of this is in tiny, so you can't really see. So what I've shown you here is the steps of the original online matrix factorization algorithm. So you have 3 steps: computing the code, aggregating the sufficient statistics of the surrogate, and then minimizing the surrogate. This is how it works. Now, our algorithm does a few modifications to this algorithm. And the first thing it works on masked data. So you can see in several places there's a mask that appears, and this mask appears in different variables that we're aggregating upon. Okay. And then the second thing is that we needed to add, that goes beyond the intuition of masking is enough, is that we need to add some form of averaging, okay? Just like in stochastic gradient descent when you're doing some form of average SGD. And the goal is really to do a variance reduction. So if you add this variance reduction, which is one difference between the ICML and the journal paper, if you add this variance reduction, then A, you can prove that things do work, and B, things work better. And I'll show you this. So really, we have a few places here and there where we're really doing this variance reduction. And you can see here that there are weights. And there are weights that need to decay, and there's theory that tell you basically that the algorithm converges if the weights are between 2, if you have 2 different kind of decay plans. And in the paper, we're showing that basically in this bound, it basically always works well. So it's easy to set. Just take the middle of the bound, and it works. Okay? So this is to show you that we can do just a simple masked loss. Oh, one thing I forgot to say is that if you're doing a recommender system, you have no control on how you're doing your masking, because the unobserved data, actually you could have with the nice talk that we had before. But if you're doing a passive recommender system, you have no control. So this can it can be pretty bad for the convergence of the algorithm. Okay. So here I'm showing the difference in the tail between just doing masking or doing this variance reduction. And this is slightly subtle, but basically we can show that doing variance reduction gives you a controlled convergence, whereas just doing masking doesn't. But that's really in the tails. That's really when you go far. What we're showing here is that with this variance reduction, you really get a really good solution if you wait long enough. And it's still faster than not subsampling, okay? Okay, so why does this work? So once again, we really have an objective here as a function of D of one of the 2 matrices that's a sum of objective on functions on samples. Sorry, on samples, and this sample-specific loss is actually the minimum over alpha. Okay. And what we're doing is, as I said, we're minimizing a stochastic measurement. And the reason it's a measurement is that we're not using the optimum alpha in this work. So this is really the stochastic majorization minimization algorithm. And intuitions are each time we're computing a surrogate, which is above the function that we're trying to minimize. And then we're doing full minimization of this surrogate. Now, what we did to prove that our algorithm works is that we extended this framework to accept approximations in both of these steps. Okay? And because we're able to accept approximations, then we can start fudging with our computation and basically making things faster. And we can accept two kind of approximations. So this is actually extremely technical work, and it's really my student Arthur Mensch and Julien Méral who did this work. I mean, the proof is very technical. But really, we can accept two kind of approximations. One is we don't have to have an exact measurement. We can have something that is an approximate measurement. It doesn't always majorize. So that's actually a very powerful relaxation that we have. The only thing is that this approximation must converge to 0. So that's why we need the variance reduction to prove. And the other thing is that we can accept partial minimization. And the nice thing is that this is actually needed to prove that the algorithm that's actually implemented by Julien Méral, not the one in the paper, but the one in the code works. Because he wasn't doing exact minimization, and now we can show that it's not necessary as long as the error decreases fast enough. Okay? So to conclude on this part of the talk, really the take-home messages are when we have matrices that are very big in both directions, the idea is that we can be online in one direction and we can do subsampling in the other one. And I suspect that this trick carries over to a bunch of different problems. And recently, only very recently, I've realized that stochastic MM and stochastic EM were related. And so you can probably apply this trick where you're applying stochastic EMs. And so we've observed 10x speed up on an algorithm that was already state of the art. So that's pretty good, I claim. The analysis uses stochastic approximate majorization minimization. Okay? So now I want to switch to a different kind of problem, which is the problem when you have categories that are not well controlled and that create a huge dimensionality. So it's another line of research that's only weakly related to brain imaging. And this is work that's done by Patricio Cerda and with Balázs Kegel. And this is where there's some machine learning in the real world. Basically, almost every machine learning paper starts by assuming the data is vector data. And then when you work with data, you get data like this. The challenge here is the categorical part. And there are different points of view on this, by the way. This can be seen as a data cleaning problem. This can be seen as a feature engineering problem. I see this as a problem of representations in high-dimensional spaces. Why data cleaning problem? This is I'll go back to this, but this is a classic problem where you might want. It's not obvious in this example, but in other examples. You might want to merge categories. You might want to normalize categories. So typically the reason why you have, actually this is this slide. Typically the reason why you have an explosion, when you really have categorical data, it's not separate users, it's really categorical data, but you have an explosion of the number of categories, is because they're not curated. And because you have many different expressions that relate to the same thing or similar things. And so typically the database literature tackles this with various approaches such as deduplication or some form of named entity recognition to try to clean this. But yeah, I'll go a bit more over the related work. So I like to call this the problem of dirty categories, is you're giving things that they're categorish data. They're a bit like categories, but they're not exactly categories. And I mean, one thing that we do in the lab is that we develop a toolkit that's known as scikit-learn, and users of scikit-learn often have this problem. So this is one thing that interests me. So the problems that underlie here are that the categories might be overlapping. Here, this is the real data where we have different kind of police officers. And so there are different kind of police officers, but to a human, they're related. One clear problem is that it gives a huge cardinality, and some of the categories are extremely rare. Sometimes you only observe one category, and you might have new categories in the test set. So this is present in a lot of real-world data. So typically things like looking at employee salary. This is a public data set. Looking at this is a data set by ProPublica that is related to finding which payments to doctors are fraudulent. Basically, when are pharmaceutical companies trying to bribe doctors? If you look at this data, this is a largish data. If you look at this data and you look at all the categories, all the company names that have the name Sire in it, and this is the list. And so basically, most entries are Sire Inc. And then you've got different variants. Okay, so this is why it might be seen as a data cleaning problem. The traditional point of view would be, okay, merge all these, and it might be the right thing to do, but it's a difficult problem. And so we've looked at a bunch of different problems, and we've collected these. And so an interesting thing is that nothing on UCI machine learning has this structure because they're all curated. People give you the curated data, and they spend a huge time curating the data. We would like to work on non-curated data. And across many different data sets, we've looked at the cardinality of basically the number of categories with an increase of the numbers of row. So subsampling randomly. And so what we're seeing is that many data sets, we have the cardinality of the categorical data that increases with the amount of data. So it increases sublinearly, and this is why I'm calling this categorical data or categorish data, because it's not the same thing as your users or your different entities in a recommender system. You have shared information across those strings. So really the goal of this research is to give a view of supervised learning on dirty categories. And this is where I make another opposition to data cleaning. We are not trying to merge those categories. We're not interested in this. We're trying to work directly on the dirty categories and to solve an analysis question. And here, this is why we think that we can outperform a standard database cleaning approaches, because we have some signal that will guide us. And typically, in the data that I've shown you before, should we be merging Sire Corporation Hong Kong and its Korean branch or not? Maybe they're not behaving the same way in terms of fraud. So maybe we shouldn't, or maybe we should. And the analytic question should inform us on this. So that's really the overall goal of this line of research, and I'm going to present you a simple step in this direction. So in terms of related work, well, there's all the work in database cleaning that I've mentioned quite a few times. Recognizing and merging entities from different sources. This is known as record linkage. Matching entities that should be the same across the same source. This is a deduplication or fuzzy matching problem. And so there are many different problems, many different approaches, but basically they're either unsupervised or they require known matches. Okay? And we want to do a third thing here. And their goal is to output a clean database. That's not our goal. Then there are related solutions in the natural language processing. So you could see this as a normalization problem. But the problem here is that this requires a set of rules, and typically you handcraft them. So each time you have a new problem, you're working in a hospital, you're working in a company, you need to redo the rules. This is also related to semantic problem. So basically, we're trying to relate different discrete entities. Clearly approaches related to distributional semantics would work here. The problem is that we typically don't have enough data. So distributional semantics or word vectors work well when you have a huge amount of data. And on a given data set from a given company, we're going to have, what, 10,000, 100,000 rows, maybe a million. But this is not the size of Wikipedia. And also the vocabulary is domain specific with specific acronyms or things like this. So it's not obvious. I mean, you can't basically take a pre-trained word vector. But there's probably things to borrow from there. And the other thing that's been developed a lot lately is character level NLP. Because basically character level NLP is robust to typos. And I'll show that we're sharing, our solutions share some work with character level NLP. That said, if you're doing a recommendation for buying and your user has typed London or your user has typed Londres, which really denote the same entity, there might be a signal here. It might tell you where the user is living, and there might be a signal that you might want to use. So once again, I claim that merging entities without the supervised signal may not be the good thing. So the solution is a very simple one. It's basically we're going to take one-hot encoding, and we're going to adapt it to add similarities to it, okay? And the reason why I like this as a machine learner is that basically one-hot encoding maps categories to vector spaces, and once I'm in vector spaces, I'm happy I can do my math. But also string similarities do happen to capture a lot of information. So really the core intuition is the following. This is a standard one-hot encoding. The problems are it doesn't scale well with a huge number of categories, and you don't know what to do with new categories. So we're really replacing this 0-1 similarity by continuous similarity, and we're using this. So it's really trivial. It must have been done before. It's just not has been studied, or at least we couldn't find a publication studying it. So we did experiments with a bunch of different string similarities, and you can look at edit distances, you can look at the standard string similarity used in lead application, or you can look at n-gram similarity. So basically it's character level n-grams. You're counting how many character level n-grams you have in common versus how many character level n-grams are total in between two strings. Okay, we've applied this to a variety of different data sets, and it's actually a lot of work to find those data sets because people don't put those data sets public. So if you have a non-curated data set that you're willing to share, we're interested. And they all led to different kind of prediction problems. And all those data sets are open, and so we're trying to put out a benchmark. And really our experimental paradigm is quite stupid, is we're doing cross-validation, and we're looking at how well things predict. And so we compared a bunch of different categorical encoding approaches, and we did a few more, but I'm really giving you the main idea. And we did this on all the different data sets that we had. So this graph is a bit hard to read, but my goal here is to give conclusions that go beyond a single data set. And what I'm reporting here is the average rank of an approach over all the data sets. So smaller is better here. And so basically what you're seeing is that on average, similarity encoding with 3-gram similarity outperformed the rest by some margin. But it was almost always the best. And in general, similarity encoding outperform other approaches. And so this was with gradient boosted regression trees. If we do this with linear models, the conclusion stays the same. And so if we do this across a variety of different learners, supervised learners, we find that almost systematically taking similarity in account compared to one-hot encoding gives a boost, okay, across many different data sets. So this begs the question, did we just reinvent string kernels? And at some point I thought we had, but we didn't, because if you look at the inner product that is defined by our encoding, our feature vector, it's really the sum over the categories of the training set of the similarity between one instance and a category, and the similarity between the other instance and the category. Okay, so it's not just a string similarity, and This is extremely important because what we're seeing here is that the categories in the train set actually shape the similarity in a specific way. And so if we compare our approach to a bag of 3 gram, which is basically an encoding method that approximates string similarity, we find that we significantly outperform it, okay? So this is important. The fact that we're not just doing standard string kernels is important. Okay, one problem that we didn't tackle here is the fact that we have a huge dimensionality, right? Because we still have this huge dimensionality. So this gives us statistical and computational problem. So really the simplest way to tackle huge dimensionality is to do random projections. And what's really interesting is that with one-hot encoding, random projections actually improve prediction. And the reason is basically because we do have some low-dimensional subspace of these categories, and random projections are pretty good at capturing this. So we also looked at some simple form of deduplication. So we compared, because deduplication can be seen as a data reduction, okay? Because you're merging categories, and so you're doing deduplication plus one-hot encoding, so you're getting a much smaller one-hot encoded matrices. And then we looked at different data reductions of 3 gram similarity encoding, including just random projection on these guys, okay? So what I like about random projection is it's stateless, it's extremely not costly. So this is extremely scalable. So once again, we did this across many data sets. And so the thing that does work better is not reducing the data, but we find that reducing with either k-means or random projection also works very well and outperforms all the other approaches. So outperform our solution to deduplication. So we're not deduplication experts, so maybe we did it wrong, but this is terribly easy to do. It requires just no knowledge of the problem. So I want to do 2 comments here. One is that if instead of doing random projections, we did matrix factorizations on these problems, we would be basically reinventing multiple correspondence analysis, which is something well known to find structures in categorical data. And so this gives us the intuition that we can probably improve multiple corresponding analysis or improve this approach by either adding similarities to multiple correspondence analysis or doing matrix factorization in here, okay? Which is, and this establishes a link to the previous part of my talk. And the other thing is that if we want to make this very scalable, it's completely possible. And what we need to do is simply we need to use the hashing trick for n-grams. And this is going to give us 2 things. It's going to give us speed because we're going to be able to pre-allocate memory and know exactly the dimensionality of our problem. So we can do this basically streaming with only one pass on the data. And the other thing is that when we compute our hash, if we take small hash functions, we're going to create collisions. And those collisions should behave basically like those random projections and should allow us to be very scalable. So this, by the way, is work in progress. But as we started doing this, we started understanding more things, and we've actually gone much further in terms of work here. And I can't give you the results because we're still working on this, but basically we're working on a probabilistic model of n-grams that basically explains the form of the inner product that we're seeing. And we have good hope to have something that is both scalable but not magical, where we can tell you why this works with a probabilistic model of variations in categories. So this is all I have. Really, the underlying ideas of my talk are very simple, and it's really the idea that across a set of different problems, when you're in very high dimension, you need to find some better representation than the original data, and you can do this via factorizations or similarities. I showed you how to make factorization fast, really using subsampling. And by the way, there is code available on Arthur's GitHub if you want to use this. And I also showed you a very simple approach to work with dirty categorical data. And where this research is going is really that we hope to create a category-aware metric space and to do the analysis in this category-aware metric space. And there's also code that is available. And this part of my research is motivated by the Dirty Data project, where our goal is to make analysis on non-curated data easier, requiring less manual work and less domain expertise, and we're hiring there. Thank you.
Here you go.
So on the second part of your presentation, I will just make the hint of looking at similarity joints.
Okay.
You may find this is a big, let's say, research area in databases,
yeah.
Or you can find both similarity metrics for comparing the tokens, but also, and most importantly, algorithms for avoiding comparing everything with everything, okay?
Yeah.
Which is suggested by this approach you present. But this is just a parenthesis.
Yeah.
On the first part of your talk, I had the impression that the cascading, let's say, method you are proposing on treating the features in one dimension, okay, is very similar to forward selection. Algorithm, actually you have a seed and then you just add. And we know that forward selection is vulnerable to local minimal. So this
approach is vulnerable to local minimum, but I think I know a bit about forward selection, and I think we're quite significantly different.
In what sense?
This is minimizing a cost function on which we can play quite easily. We do have guarantees on the expectation of the minimization. Those guarantees work in practice. I mean, I've shown you that we're really able to minimize this really well. So of course we're sensitive to initialization, to local minima. But one thing that we can do, at least in the signal processing world, that people do a lot, is craft the penalty in a certain way that shapes the result, which we can do in some setting. And I don't think you can do this with forward selection.
Well, I'd say that in the feature selection community, they have elaborated different algorithmic patterns to deal with the problem, including hybrids of forward and backward selection, independently of the cost function. Okay.
Yeah, I think I'm reasonably aware of these things, and I mean the approaches here are both more scalable and more stable.
Okay. And the last question I have is regarding the high dimensionality. When we are talking about what we mean with high dimensional, if you take, for instance, the dimensions of the evolution of the dimensions of the data sets that are actually published in major machine learning data sites, you will see that the last, let's say, 10 years, you have an increase in terms of dimensions of 2 or 3 scales. Mm-hmm. So it means that we end up with millions of dimensions. Okay? Mm-hmm. What was the maximum, let's say, dimension size that you have played with this implementation?
So, I mean, first, in terms of, we need to be careful because I'm more aware of an increase in the number of samples. Basically, it's extremely domain specific. There are few domains that have a huge number of samples and a huge number of features. There are. As I give this talk, I hear more and more, but the typical machine learning setting is either one way or the other if you go to conferences. It's not my case, so I'm disappointed. But with regard to the subsampling approach, I would really tell you more. Just give me more. I'll just be happier. It's just the more you give me, the better these things will work. And so we've worked with millions in one direction, hundreds of thousands in the other. Millions and billions.
Astronomical stuff.
Yeah, so astronomy would probably, astronomy definitely is very large in both settings. There'd be a bit of engineering, but millions and billions should be feasible. Especially the billions. I mean, in one direction, the one in which we're streaming, we don't care. The one in which we're subsampling, We may break because if we put the subsampling ratio too big, I mean, basically the subsampling ratio depends on the amount of redundancy that there is in your data. So if your data is extremely redundant, we can subsample it like crazy. But if it's not, we can't. But still, I mean, the streaming approach, just the streaming approaches, work well on their 100,000 dimension data. They're just slow. So with a single node, not distributed, shared distributed memory, I'm pretty sure we can fit millions and billions.
Okay. Another question? More comment? No? Well, thanks again.